but it's a little bit easier to make because it interacts more directly with other fields that we know about. So in particle physics, you just can characterize everything you're looking for by how heavy it is and how it interacts, how you can make it. And the Higgs was right there where the LHC could finally find it. Higgs bosons do form very, very, very rarely, but it does happen because you have to remember everything that the Large Hadron Collider does, the universe does all the time and better. There are cosmic rays that are impacting the Earth's atmosphere with much higher energies than we can produce at the LHC. But they're up high in the Earth's atmosphere, and then the Higgs boson decays 1 zeptosecond later, so it's kind of impractical to search for new exotic particles that way. But definitely, yeah, Higgs fields are vibrating throughout the universe. There is the non-vibrating field, the background, and that is crucially important to all of particle physics. Electrons and quarks and so forth move through this Higgs-like molasses, or I should say molasses-like Higgs, and that's how they get mass. That's what makes the universe interesting. There's only a small number of fundamental ingredients of reality, and in fact, you could boil it down to 4 if you wanted to. There's gravity. There are the other forces of nature, all of which sort of have the same kind of basic structure. There's the matter particles that make up your atoms, the up and down quarks in your protons and neutrons, the electrons in your atoms. And then there's the Higgs, right? So it's one of a very, very tiny number of fundamental ingredients you need to explain the world around you. How much is it worth finding that and verifying that it's there? The only accurate answer is that it's priceless, right? It depends on how much money you have to spend on basic research, because you're not trying to cure cancer with this. You're not trying to fly to Mars or anything like that. We're not going to get jetpacks. It's not going to make a better iPhone. But it helps us understand how the world works. I mean, it's a feature of doing this kind of research that you always do get technological spin, the World Wide Web, which was a spin-off of research at CERN. But that's not why we do it. We do it because we want to understand things. And fortunately, we still have enough money to do it.
I'm not asking for a jetpack or even a cure to cancer, but has this unlocked a new level? Has this unlocked, for you guys, has it unlocked a new level, or is it the you were right, well done, pat on the back?
No, we're certainly very hopeful that it is not only a capstone achievement, but a window onto a whole new world. One of the nice things about the Higgs boson is that it's a little bit more sociable than other kinds of particles, and we know there are particles we haven't yet detected. We know that there's dark matter in the universe. If it weren't for dark matter and dark energy, we might really be worried that the particles we already knew about were all that were accessible to us. But we know that's not true. Most of the mass in our galaxy is not made of the particles that we've created here on Earth. So we're hopeful that by studying the Higgs boson, this gives us a new way of looking for other particles. The ways that the Higgs boson is produced, the way it decays, the way it becomes a force mediating interactions between dark matter particles and other particles. These are all new toys for particle physics to study and play with. This is going to be going on for 20, 30, 40 years into the future. These are some incredibly talented, hardworking, dedicated, bright human beings, the theorists, the technicians, and the experimenters who built the theories and built the Large Hadron Collider. And they've devoted their lives, literally, to looking for a particle that may or may not be it. And that when you find it, is not going to make you any richer. It's just going to make you a little bit happier that you found it. So I wanted to get across why this was so crucial, and why physicists in the United States were crushed with disappointment when Congress in 1993 canceled the United States' competitor to the Large Hadron Collider, the superconducting super collider. Why physicists are still a little bit on tenterhooks about will there ever be another particle accelerator to the scale of the LHC. They devote their lives to it, but theorists might spend their entire life working on a theory that the accelerator then says isn't true. You have to learn to deal with that. But you then get these pictures of Peter Higgs and Francois Anglaire and other physicists who came up with the idea of the Higgs boson back in 1964, and they got to be in the room in 2012 when the experimenters told them, you weren't. That is part of it. And that is a kind of sweet, triumphant success that we can rarely experience as humans.
For me, it's really an incredible thing that has happened in my lifetime.
As a cosmologist who's alive at this time, you're very fortunate. you've got to enjoy this announcement. You won't live forever, I'm sure. Does it frustrate you that those next things, those things that are 40, 50, 60 years away, just beyond your lifetime, you never get to see? You have to think about that.
Well, I think that the great thing about science is that we almost are always focused on what we don't yet understand. And sometimes the new understandings come fast and furious. There are times like the 1920s when quantum mechanics was being put together when it's hard to imagine what it must have been like. When I wrote my book about the arrow of time, I delved into the work in statistical mechanics and thermodynamics in the 1870s. And the debates there are just fascinating to read. They didn't know it was really fundamental stuff, and they were building it from scratch, and some people didn't believe in atoms at all, right? And other people were using atoms to explain everything. And now in particle physics, we put the capstone on the standard model, and we're hoping to find dark matter. In cosmology, we found dark matter and dark energy. I can't say over the next 10 years, 50 years, are we going to be strewn with new, shocking experimental results, or are we just going to be, fine-tuning the understandings we already have? I think the fact that we don't know which of those is going to happen is part of what actually makes sense.
But I think about someone like Albert Einstein or Niels Bohr, and I kind of think, gee, I wish I could just tell those guys what we found out a few weeks ago. They would have been so happy to know about that.
That's my pet farm.
And it'll be the same for you when you're going like,
It's not
I
really
wish
a
I
pet,
could tell
obviously.
Sean about this thing. He would have loved to know that. Does that eat away?
It does not, actually, because you could say that about anybody, right? You could say, what would Einstein have told Newton? But, Newton had his own fun, right? He got to invent physics, basically, right? I mean, Newton could have told Galileo things, but Galileo did his own thing. I think that every generation gets to apply the talent it has.
Moon's out as well.
And right now in science, not just physics and cosmology, but overall, there's so many great problems and so much interesting data coming in that we are at no loss for interesting questions to study.
Yeah, that's that white light up there. It's probably not a very good picture. That's the moon.
The thing that we teach our students in the textbook.
Not Moon the cat, but Moon the moon.
Why is the Higgs boson? It's what gives everything mass.
We weren't made of massive particles which fly around at the speed of light. Some people would like that, but you'd never join together to form bodies again. So it's very important that we've got masses.
At first light, everything should go at the speed of light, and you've got to stop things going at the speed of light. Otherwise, they're all whizzing apart, not interacting. So you have to put a term in which allows for a mass, which will slow it down a bit.
But different particles have got different masses. If you just think of the standard particles in the universe, the electron, for example, and say the quarks, the top quark, there's a difference of about a factor of 350,000 between the mass of the electron and the mass of the top quark, and yet those are in the same family of particles that make up the standard model. And why?
It's a particle. It's also what we call a field, which is sort of it permeates all regions of space.
It's one of those things which is very esoteric, off the end of the maths that most people can deal with, and off the end of the maths that most theoretical physics people can deal with.
The particle is just the end product, if you like. The big thing you talk about, that the particle physicists are interested in, is the field. The field is the concept of this object that permeates the whole universe.
If it's found, it gives a basis for cosmology and masses of particles, so that we become more secure in our ideas of what the universe is made of.
And this is the difference between the field and the particle. The particles, if you like, are the fluctuations, the oscillations in that background field. So it's the equivalent of, with electromagnetism, we think of the electromagnetic field pervading the universe. Its fluctuations are the photons. The photons of light are the fluctuations in that field, and that's what the equivalent of the boson, the particles, are. They're the fluctuations in this field, and then you can imagine you need quite a lot of energy to get the field to get excited enough to produce those bosons in the first place, and that's what the collision of the protons can do to you.
What happens when two protons collide at tremendous energies that makes the Higgs boson show its face?
Well, I guess so the way the Higgs has appeared in this is that you get this collision, you create particles, which then can annihilate, and you get a series of events happening. Now, if you get enough of those, then rare stuff can happen.
Is she coming back?
Okay, and what's one of the rare things that happens, that may have happened, we think, is that a Higgs particle decayed into two photons, and that's what we detected. But in a way that only the Higgs would have done. So that's how we detected it.
Can I make a suggestion then? Why aren't we searching for the Higgs field? Why aren't we searching for the particles if they're so hard to find?
Because the field is even harder. That's the problem. So we're hoping that by finding the particles, we'll actually gain some information about the field. I cannot explain it simply to the general public because it is, well, I would use the word recondite, and that means that it's so obscure that you have to go and look up the words and the meaning in a dictionary. And that is the difficulty. You have to use a mathematical language which is rather obscure in order to get to grips with it. And you have to have a mental picture. I mean, the one that's used, you'll find my colleagues love this, is a Mexican hat.
Can I bring my hat into this at this point? Well, this is where the Higgs lives. The Higgs lives on this hat.
And you imagine there's a potential that runs down and then has a minimum around here.
My finger is the Higgs. So you start out, and it's in this point here. This hat is what we call the Higgs potential. It sort of controls what the Higgs is doing. So, you know, just think of the Higgs as being like a little ball on this hat, and it's rolling around. So at the top here, okay, it's unstable because, you know, the excitation is unstable because if you nudge it a little bit, it's going to fall down the hat. Okay. Now that happens, it rolls down. You get a process what we call spontaneous symmetry breaking. Then the Higgs ends up down here. Okay, and then the excitations around that point here, this point at the bottom of the hill, if you like, at the bottom of the hat, those are what we call the Higgs particles. And it's the properties of the excitation around this point also give mass to everything else.
That doesn't mean anything to you, but to people in the field, they would know roughly whether I got it right for a start, I'm not sure I got it right, and whether this is the right physics. And it is the oscillation in a symmetric well which has a certain symmetry which causes the Higgs boson.
So the Higgs particle is a very unstable particle, and that's part of the issue, right? If it was really stable, they'd be all out there, and you'd just be able to find them. So let me give you an idea of how difficult it is to generate them. There are, on average, 200 million collisions a second between the protons and the going one way and the other way. So two protons smashed together, and that's happening 200 million times a second. Right? The accelerator's been running for about the best part of a year. 200 million collisions a second. Do you know how many Higgs have been detected? How many potentially have been detected in this data? In some of the channels, 3. So these are small statistics, right? Because they're very difficult to produce these particles and then be guaranteed that you'd be fairly confident that you've seen it, because you need a lot of energy to produce them, and then they decay very rapidly, and you have to be fairly confident that you understand the decay products in order to reconstruct what you think is the Higgs in the first place. So there are many protons colliding and very relatively few Higgs being produced. There's lots of other stuff being produced which is far easier.
There was a Conservative MP, William Waldegrave, who asked for people to write one page of A4 to explain the Higgs boson to the public, and there was a competition. Somebody won it. And you can't really do that. That's what you're asking me to do. One page of A4, written simply, and talk about Mrs. Thatcher moving through a party and everybody coming towards her and making a mass around it.
Well, I can give you an analogy for how the Higgs mechanism works. So the mechanism, the analogy people normally use is if they say, well, imagine a room, right, I don't know, in Hollywood or something, right, and the room's empty, and you get some superstar like, I don't know, Brad Pitt walks into that room, and there's no one in the room, so he can walk about freely, there's no problem. Okay. Now you go later on in the day, and the room is filled with people. Okay. Let's call them Higgs people, if you like. Right. Now Brad Pitt walks into that room, and he can't so easily move about because everywhere he goes, he gets surrounded by these Higgs people who sort of want to talk to him, want to be with him, want to associate themselves with him. And so, if you like, it's difficult for him to move about. It's like he's got sort of a lot of mass. If you like, that's the analogy of the Higgs mechanism. It's like you permeate space with this particle. So rather than being here, it's down here, and then that gives mass. Everything else sort of absorbs the mass from that.
That's not it at all. You have to talk about broken gauge symmetry and different groups and all sorts of things which are too abstract for even undergraduates. We don't teach them that. It is a difficult subject for undergraduates. You need a schooling in this subject before it makes any sense.
What happened last week?
What happened last week? Well, I don't want to say that they discovered the Higgs boson because they didn't discover it, but there was a smoking gun, shall we say.
So last week was the sort of the preliminary set of data. That's really important, right? Because there's a risk that everyone will say, this is it now, it's all done. This is a preliminary set of data, which is kind of the culmination of the initial runs that were done throughout this year, up until I think about October. Runs of the LHC, protons going around the LHC and looking at the collisions. And two groups announced results, two of the experiments, the ATLAS experiment and the CMS experiment, and both were specifically looking for signatures of the Higgs particle. And they've both seen what look like excess events. That means events above what the background would be and above what you would naturally think you should get from the standard model. And these events are at over a certain mass range, as I said, about 125 times the mass of the proton. And what they're hoping is that as more and more data is taken, the significance of these events, well, it will either grow, so they'll see more and more of these events building above the background, like a volcano rising up. Or, if these events are not really due to a Higgs, what they'll see over the course of the next few months is these events basically disappearing back into the background noise again.
I guess what would have been more interesting is if they hadn't found it, right? Because then we'd be thinking, oh, right, okay, where did all this mass come from?
So, of course, it's the Higgs particle. That's after Peter Higgs, the particle physicist in Edinburgh.
I got Higgs here, if I can find it. This is 1964, Peter Higgs, Broken Symmetries. That's the paper where he comes up with a version which is written in the language of particle theories, which is Lagrangians and covariant derivatives and all sorts of frightening mathematics. I mean, it's frightening for me because I'm not used to this language.
This work was done back in the 1960s, okay? It's actually, I was thinking about this earlier today, that it just shows you, that you work on the topical things, you work on the exciting things. In the 1960s, people were working on the standard model. And of course, they realized there was this problem with the masses of the gauge particles, and they knew they had to come up with a mechanism to give the gauge particles masses. The standard model had them all massless. So not surprisingly, it wasn't just Peter Higgs working on this. There was a group, Brout and Ongley were working on it in Belgium, and then there was a group of 3 people working on it at Imperial College, including a good friend of mine, Tom Kibble. And the papers, they were working independently of each other on different aspects of it. And in fact, the papers all appeared within a few months of each other, in fact, almost a few weeks of each other.
It will always be known as the Higgs mechanism in the community, and it will be outrageous if he's not rewarded. But if the Higgs boson hasn't been discovered, no prizes will be awarded. So it's contingent, it depends on whether they actually see it. If they do see it, it's going to be somebody in that group.
Who would you give the credit to? I remember at one stage when it used to be called the Higgs-Kibble mechanism, and then it became the Higgs mechanism, and who knows where it, I mean, it looks, of course it looks like it's got to go to Higgs if a prize is given, but there's this crazy rule, I think, in the Nobel panel, which is it's meant to go to no more than 3 people. Well, Brout sadly died earlier this year. Historically, the order in terms of publications is Brout and Ongley, then Higgs, and then Kibble and his collaborators. And so you've potentially got Higgs and Ongley, and then you've got the 3 collaborators.
Difficult call. I'm not going to call it. But one of them, 3 of them should get it.
I think they should abandon this 3 people maximum and give it to the whole 5 of them. Yeah, it's such an exciting.
Well, you can't see her, but she's sat about 10 feet away from me, cleaning herself. Like a cat. Here she comes. She's hanging around. I need a back camera, that's for sure. There she comes again. She's off now.